Okay, class begin. Class begin. Yeah. UML. Let's continue about UML. Okay, so we were talking about class diagram. So far, I still receive questions regarding this class diagram. Okay, so let's have a review about class diagram. What do we have in class diagram? So we have a class, right? So let me pour out the example. I should go here. Maybe it's this day. Yeah, here's an example here. A class diagram. This is a simple, easy class diagram. Yeah. Class diagram. First thing first, classes are there. Classes has those names of the class, has the attributes of the class, has the operation of the class. This is easy and it's not confusing at all. What confusing is, and more important is, the relations between the classes, right? So far, can you name some of the relations we learned in class diagram? Aggregation. Generalization. In other words, generalization is the inheritance, and the aggregation is the has a relation, composition. Okay, and association. Yes, association. Also, another one is dependency. The dashed lines. Okay, so only these four basic types of relations between these classes. So the class diagram is we have classes and we specify between those pairs what are the relations. Okay, so here we have, what do we have here? Yeah, this is simply associations. Okay, so association, let's start with association. Association means these two class, it's somehow they are associated. Okay, and upon the association you can add more information there, like the numbers there. That means the relations, like one-to-one relation, like could be the one remote has one dog door there. Okay, and here allow bark. The dog door has the bark, but it has many of them, more than one of them. Okay, more than one of the bark. So we have the number there representing the mapping. Maybe it's one-to-one mapping, it's one-to-many mapping. Okay. Also, there's some text there. You see, door, allowed barks. This thing, maybe it's a little bit confusing. Okay. Let's look at here. The door here, from the remote to the dog door, association from remote to the dog door. It has a text there called door, D-O-O-R here. What does that mean? Yeah, okay, in the remote class. We have something in the remote class, okay? This means... Yeah, this means the remote has a reference called door. And this reference is of the type dog door. Okay, so in another word, what is reference? Maybe it's another confusing word. Reference. Okay, reference basically it's it's a thing that you use in the class. If you have a reference to something, you can access. For example, if A has a if class A has reference to an object of class B, that is actually you can access the object of class B through the class A. Okay. In other words, reference is an attribute of the class. So here we say the remote has a reference called door, That means this remote actually has an attribute called door, and this attribute is of the type dog door. You can either put this door as the text here on this association, or you can put this door. You can remove it from here, put it into this area, the attributes of the remote. Okay, maybe this is some little bit confusing, but this means this is another two way to express the same meaning, that remote has an attribute door, and the door, the type of the door is dog door. Okay.
I have a question.
Yes.
Now, the remote and the dog door, they have a one-to-one relationship, right?
Yeah.
But we don't have a one indicated on the remote side of the diagram.
They don't have.
Yeah. If you do not specify that, we can just
one?
think that's one. Yeah.
Okay.
We can just think that's one. But here, because here it's dog door to bark, it is many here, right?
Yeah.
So it's one to many.
Okay.
So you do not have to always like specify that. Yeah. So that's the association. Okay. Association means they're somehow associated. And how they associated is one of the class has access to the other class. Okay? Like remote has access to dog door through its attribute door. Okay? Hope that's clear. Okay. And another class diagram. Let me see if I can find this class diagram. Another relation is inheritance, or we can say it's what's the word? Inheritance. What's the word? Generalization. Yeah, suddenly out of my mind. Inheritance and generalization, they're the same thing. Okay. Let me pull out. Let's see. It's not here. Okay, here. See. Okay. Well, this is a generalization, or we use different words for generalization. Inheritance, generalization. Sometimes we say it's is a relation. Okay, but they are the same thing. Here, this is a notation. It's a triangle and a line here. So the triangle is in the superclass, and the other end of the line is a subclass. Okay. This means student is inherited from the registration user. Student is a registration user. Student has all these attributes and operations, behaviors from the registration user. Okay, and you can implement student with some additional attributes or override some of the method. Okay, and likewise, the professor is also a registration user. Okay, professor class inherited from the registration user. All right. So do we know what is inheritance? Right, we know that. Yes. Inheritance means like we have two class. If we have superclass, we have a subclass. So if subclass is inherited from the superclass, that means the subclass get all these attributes, get all these behaviors from the subclass. Okay. Superclass, yeah. Subclass get things from superclass. Get information from superclass. Okay, like human. Let's use human as a superclass. A student is human, right? A student is a human, so we can inherit it. We can use inheritance, like student get like eyes, nose, head, something like that. Okay, students human. Professors inherit from human. Okay, and some other like and other employees. Okay, inherited from human. We are all human, so we can inherit from that class. To inherit its attributes like eye, nose, mouth, and behaviors, maybe walking, running, these things. Okay, so that's inheritance. We represent this kind of inheritance with this triangle and this line here. All right, and another one is called compensation, aggregation. Well, different words, but they're the same meaning. Aggregation, compensation, or has a relation, which is something like this diamond and a line. Okay, the diamond is on the side of the owner. I guess that's the owner. Like the course. This is another good example. Let me pick another one. This is the only class diagram here. That's fine. Okay, maybe we have another example right here. The course is the owner and the course offering. Course is an abstract class. Maybe not abstract class. It's more abstract. It's a course, just like where SWE. I forgot the course number. We are SWE 6743. Okay, course SW 6743. So, and a lot of professors are offering this course. I'm one of them. And so this course offering may be referring to this course I'm offering right now in this room. Okay, we have a location, 8 students to the course. And the course actually has a course offering. Okay, maybe it has something else. It has another class called prerequisite. Like has a prerequisite, or like a car has a wheel, 4 wheels. Okay, maybe it's more wheel. A car has a steering wheel. A car has a shield, something like that. Okay, so that has a relation. That means, well, this class, this owner, this is owner, and we have something else that maybe provides some service, or it's just a part of that owner class. Okay, the owner class has this diamond here, and then we have a line. The other end of a line is maybe the parts, or you want whatever you want. How you understand that there's a part of the car, a part of a human being, something like that. That's has a relation. Okay. And this dash line, dashed arrow line and arrow, this actually represents a dependency. Dependency means, okay, this, for example, here, this registration manager depend on the schedule algorithm. Okay, what do we mean by dependency? But depend, that means if we have something change in schedule algorithm, it may affect the registration manager class. Okay, change in the dependent well, if A depends on B, okay, change in B will have some effects in A, okay. But here, let's say inheritance. If we have something change to student, will that have influence in the registration user? No. Right? If we have something change in student, will it have some effect to human? No. Okay. And course offering, if we change the location of the course offering, it won't change the course. Something like that, right? Okay. Yeah, that's dependency. And also this association has this type of association which have the direction. Okay, sometimes we don't have a direction. Maybe it's a mutually association. Okay, like registration form. Maybe it's here. The student has course offering. Course offering also has student information there, right? So it's maybe mutually association. So you can give it direction or not, right? So that's association. Association again, association somehow associated, and if you put more information here, it'll work because this information means we have a reference to the door, which is of a type dog door, or we can see we have attributes called door, which is of the type dog door. Okay.
So association has open arrow when it is directed, right?
Yes. Well, yeah. Don't mix that with this
Yes.
inheritance. Inheritance is a solid triangle there. Maybe it's arrow, but it's not open arrow. Yes. So that's the relations of these classes. Okay, of these classes. All right. So we've learned a lot about classes. Yeah, we talk about what classes cannot do, right? So like it cannot have those implementations details, like the algorithm, something like that. Another thing for the class diagram, another feature of class diagram is, do you think class diagram is dynamic or static? Static. So is it static? Is it dynamic? Can you give some reason why it is static?
It's more like
That's showing
Class
doesn't change.
diagram is static.
Yeah. It doesn't change unless you're adding to it. It's still the same.
Yeah. So for those who said dynamic, can you give me some reason?
Change attributes.
It change attributes.
Change some attributes in the class diagram.
You can change attributes
Yes.
in class diagram. But we can change everything. We can.
You
Yeah.
can change everything.
Yeah, well, we can change our design. I mean, if we have some design, we can change,
But
right?
you can implement some things in the class diagram and make a change.
Yeah, like here we can change the user's name to something else.
Yes.
Is that what you say? Yeah, that means you are changing the design. You are changing the design of that class. Yes.
One way speaking, I mean, like now, student object, the student class may be there, may not be there, right, at a point.
Yeah. So that's the point there. So, but it shows the relations of all these classes. Yes. But when the system is running, you don't know if any classes, if any objects are there, or if any objects is in which state, right? So it's not. So it's actually the answer is static. It's static. It's static. It's not because we cannot change these attributes. We cannot change it. We can change the design anytime. We can change the design because it's our design, right? To the system. If we change the design of the system, we implement another system. Yes, but I say it's static. It's because it does not reflect anything that is during runtime, right? It's a system is designed this way. We have all the classes, relations connect to each other. But when we are actually running that part, like here, the registration manager, this system, for example, maybe we do not have any student in the system or any professor in the system. It's just a new school just started, okay? We just have a registration manager, and using the scheduling algorithm, maybe prepare for the start of the school, something like that. At that moment, we do not have any maybe student, professor, or even any course is not there, okay? But the classes, they are there. Just we do not have those objects there. It's possible, right? So that thing we do not know unless we actually run the system. So class diagram is pretty dynamic. It reflects the system design dynamically and statically. But what if we want modeling something that's pretty dynamic during runtime? What should we do? That's for the week 10 stuff. Let me ask you. Let's have a review back a little bit. So when we are talking about ADT, abstract data type, one thing I said is state of the ADT. State of the ADT depends on the data, right? On the attributes or the data of that ADT. So if we have a like this cup as a class, so it has a state like lid is open, right, or closed. Maybe it's a boolean there, open, closed, true or false there. Okay, so that means it's in different state. Okay, and during a runtime, the state is changing, constantly changing. Because when I'm doing some interaction, I want to refill this cup, I will change the state to like open, and then refill it. Only when it's open, I can use another class called water fountain to refill it. If it's not open, if it's in closed state, I cannot just use the water fountain class to doing the refill. So that's pretty dynamic, and it's happening during runtime, which class diagram do not have those information. So we need the state. We need the state, right? So that's why we are going to introduce state diagram. Okay, anyone of you know what is state diagram? I think I mentioned that a little bit. It's empty, need refill. Modeling real-time systems with the state diagrams, with the state diagram, yes. So because we have a lot of things that is running during real-time, runtime, like I suddenly feel thirsty, I need to go to there to do some refill in my cup, some water or coffee. And if you refill water or coffee, it depends on if it's in the morning or it's a sleeping time. Okay, if it's sleeping time, you maybe you do not refill coffee. Maybe milk is better. So while this thing has a lot of it's dependent on a lot of things, a lot of other conditions there. So it's pretty complicated real time when the system is running in real time. Okay, so we're trying to have another thing, state diagram, to help us with this kind of task. All right, so we want to model in the real-time system. So think about the real-time system. You have any idea what is a real-time system?
Real-time systems could be embedded systems. Yeah, embedded system.
Yeah, it could be. Yeah, embedded system is one of the real-time system. And maybe if you think purely software,
Yeah.
embedded system. Well, let me give you a good example. Think about Uber. You all know what Uber is, right?
Yeah.
Yeah.
Banking.
Yeah, maybe
What about banking?
banking. Usually when we talk about banking, we refer more to maybe some database system or, but Uber is a very good example.
And ATM based and all that would be
Yeah, that could be another example, but I prefer the Uber. Yeah.
Is that dependent upon like how often the data that's displayed to you is updated?
No,
Some sort of constraint for that?
it's here. Characteristics of real-time system. Okay, let me talk about this. So reliability, which the most important thing is the timeliness. So within a specific time limit, you have to have some response. Maybe banking system, yeah, I guess, but sometimes you just deposit it like occurred after several hours. That happens, right? So
like
maybe it's
withdrawal has to be immediate.
okay.
Right?
Yeah, could be, yeah. Right. So, well, that's not a good example of real time. But when we think about real time, it's really something that immediately. Okay.
The registration system and all would be, right? Or even that, like ticket registration.
Real-time database.
Yeah, real time database. That's kind of like the concept. If you use the word real time, that really means the time, like constantly, instantly give you some position and the process. Okay, responsiveness. Okay, responsiveness means randomly ordered events. Maybe you held a taxi here before it arrives. Maybe another person is held a taxi there. If you two are doing some couple, okay, the system doing a calculation for you, ask you, okay, you have this couple option which will save you like $20 for your ticket, something like that. Okay, concurrency. Okay, concurrency, and dynamic structure and behavior. And sometimes it's distributed system. A dynamic structure and behavior means it needs some input. It does not necessarily result in the same output. It depends on some other input and situation conditions. Okay, that's a real-time system. It's pretty complex. Okay, so we need some tool to help us to make it pretty clear to us. Otherwise, if we're confused, it's hard to like implement this thing. All right, to clarify that a little bit. Yeah. We have two different types of them. It's a hard real-time system and soft real-time system. So if your example is the hard real-time, you have to guarantee the response time. Okay, like the flight control system. You cannot just say we need maybe 1 minute to. Okay, so the CPU is like running the flight control system, and at the same time maybe some other task come. You still have to maintain this flight control, otherwise it will have some severe consequence. And then the soft real-time system. We can have the priority to have a maybe different reaction. So it's more dynamic. We don't have to reinforce. We don't have to guarantee that. But still, it's real-time system. We still want the feedback. But if some other higher priority things happens, maybe something will change. Like, okay, here, you're making cars. Sometimes it break. It happens, right? But you don't have to guarantee that. Okay, the real-time system like cruise control, auto driving, all right, Uber, all those are real-time. real-time instant reaction. Okay. And the more important thing is the events can be unpredictable. Right? You don't know what's going to happen when you're running the Uber system. Okay, and the server is running the Uber, and we don't know we don't know at this point will that be somebody that hail a taxi at this moment. We don't know that. We just, when it happens, we have the reaction, but we don't know when and where that will happen, right? So it's pretty dynamic. It's pretty random, those events. And events don't stop and wait, right? So you can just do some mapping. You cannot map everything from every user, because we have a whole bunch of different ways to use the system. We want to go from school to home. Like we ask for a taxi, or we need a taxi just from school to the grocery store, and then from grocery store to home. Yeah, somehow it's hard. Well, if you think about the big data thing, okay, it may be predictable, but that's another story. But the real-time system, we assume that the things happens we cannot just predict. So we want to provide this solution that can have reaction to those unpredictable events, right? So we want to have a way to model that. Yeah, so change is the rule, dynamic structure of the behavior. Adapt to change, yeah. And modeling change structures and the behaviors. So we want to adapt to change. But if we think about the class diagram, it doesn't. It's static. Since it's static, well, it's hard to adapt to the change, and it just doesn't give you those information. Okay, like when this happens, should I call which class? Should I call which method? And this class is in which state? It just doesn't give you this information. Yes, and the real-time system must have state. Yeah. Because if we think about this input, all those random events that happen, okay, every event will trigger something, but these events, we need some example. It's easier to understand. Okay, so sometimes during rush hours, when you're using Uber, during rush hours, sometimes it has the option to let you maybe put a bid there. Like, I want to offer $50 from here to school. Okay, so if you put that offer in the morning, okay, during non-rush hours, a driver may come and pick you up to home. Okay, but if you offer that $50 during rush hours, and another person is offering $60 during rush hours, the car won't gonna be here and pick you. Instead, it's gonna pick the other person who put a higher price there. Okay, but here the events here is the same. All right, events here is I offer $50 to go from school to home. The events remains the same, but the reaction of the system, is it the same? No, because the system is in different state. Right? In another way, the system is in the like general hours, the state general state. And this, in the second case, the system is in rush hours state. Okay, system is in different state. If you have the same events in different state, it will result in different reaction from the system. Another example is a microwave. If the microwave is in the running state, if you hit the stop, what's going to happen?
Stop.
Yeah, it's going to stop. Alright, this is not a good example. Well, yeah, maybe that's still the microwave. If it's in a state of running, if you open that door, it will stop and open the door for you, right? The light may turn on, something like that. But if it's not in the running mode, it's in like idle. If you open the door, the reaction is different. It won't stop the system because it's already in stopped position. It won't execute the code to stop the system because it's already there. Right? So that's another same thing. The same event triggered a different reaction from the system. To model that, class diagram is not enough. We need a state diagram. Well, state diagram will give you the information that when we're in some certain state, some event happen. It will trigger you go to the other state. So that's a state diagram deal. Okay, to model this dynamically happen events and what's gonna change? What will change the system? What event can change the system? Okay, if you happen same events will trigger different change to the system. It depends on which state is the system currently in or currently on, in state or on state. Okay. So it must have state for us to model this behavior reaction, okay, of the real-time system, right? Passive objects. Passive objects. The objects supported by most object-oriented language are passive. This means the thread of execution for passive object must be supplied by the environment. Well, for these two concepts, you just need to remember that active object has its own thread. Passive object doesn't. Okay. And the active object well, receive message from other object. Yeah. Yeah, finally arrived here. And the reactive system is another concept. Just let you know that reactive system is one whose behavior is primarily characterized by its response to external stimuli. And usually these external stimuli are discrete events whose order and time, well, is random, less predictable. And reaction depends on the system's state. And the reaction may involve performing some work or change the state. That's why we need the state diagram, like finding the state machine to model in this, whatever you call it, reactive system or a real-time system, real-time reactive system, which most importantly, this system needs to provide instant feedback in a certain amount of time. And this feedback is different. This feedback is given to the events that happen externally, and most importantly, the same events doesn't always trigger the same feedback from the system. Okay, remember that. This time, at this moment, the class diagram is not enough, so we need to find a state machine. So here's some maybe definition of it. I like to go to the example, then we can look back to the definition. Oh, this is all definitions, which is tedious. We need an example. Let's see. Okay, so this is an example of state diagram. Yeah, state diagram. Sometimes you call it maybe a state chart or a state diagram, something like this. What it has is we have a whole bunch of state, and the state are connected to other state, right? And upon this connection, on this connection, we have all these events there. Like here, from this is maybe a calling the system to make a phone call. Okay. Well, it's pretty clear here, but is it better? Yeah. Okay. So initially, we have an initial state starting from this state. Okay, and then we go to some initial state that's an idle. Idle is the important state for a lot of systems. It always has some idle system, idle state, you're just waiting for something to happen. Okay, when it's in idle state, for example, and something happened, which is somebody pick up the receiver. Okay, this is events. Pick up the receiver, and then it changed from this idle to dial tone, which is you pick up a phone, it's do this kind of thing. So that state, the dial tone. Okay, and then from this dial tone, if you when system is in this state, if the event happening is start dialing, okay, then the system goes to this dialing state. All right, dialing state. All right, but when it's in the diatone state, go back here, diatone state. Or if what happened is hand up, it goes back to the idle state. Right, it's something easy to understand. Right, it's just something happened, it triggered something else. Okay. Let me see. Okay. All right. However, when it's in the some diatone, go back to this state, diatone, which is a do. At this moment, let me ask you a question. If the event happening is incoming call, another call is coming in to the system, what's going to happen when it's in diatone?
If another call is coming in, it will receive the call.
It will receive the call.
Engage.
Now use your common sense. When you're doing the dialing, it's do, and another person is calling you.
It's
No,
not,
are you on the tone or on the dial?
Engage.
but it's not idle, so would there be a
Dialing
difference
tone,
in
this state.
diagram?
The dial tone is not dialing yet, right?
Yeah, but
So it's not dialing, so it will still receive a call.
This is the call.
No, if you
This is
pick
the-
up, at that point you will not receive.
You're not gonna receive a
It's a
call.
normal phone.
Yeah.
It's not like a.
It's not a cell phone like
No.
telling you another call is coming. Okay, it's just a phone sitting there. Okay.
If you pick up,
If
For
it-
us,
it's
it will
gonna-
be just
It's a
idle,
business
right?
signal.
it's gonna go to.
Yeah, it'll stay in the dial tone, but for the other one, it'll be the busy tone.
I didn't get
For
it.
the person who is calling, it is gonna be the busy signal.
Oh yeah, for the person who's calling, they're gonna be the signal.
For
But
us-
for this system,
There's no change.
when it's in dialing tone,
It's-
if you use your common sense, there's no change, right? And also, it's the same in this state diagram. See, from this dial tone, we only have a reaction to two events. One is start dialing, it changed to the dialing state. One is hang up, it go back to the idle state. Okay, if something happen like incoming call,
You know.
nothing's gonna happen. The system won't have reaction in this state. Okay. So that means, but however, if you're in idle state, if there is an incoming call, what's gonna happen?
Right.
It's going to the ringing state. Right? It's going to the ringing state. So that's the concept. The same events does not always trigger the same reaction. Okay, so here, if you're in dialing tone, this incoming call, nothing happened. But if you're in idle state, this incoming call, it's gonna ring. Okay. Also, if you're in dialing state, like you're actually pressing the button, there's no do this on. If that's incoming call, still nothing's gonna happen.
But there is no connection between dial tone state and
Ringing state. Yes, exactly. That's because we didn't model that. We didn't model that function. This system does not have that function. If it's cell phone or something like that, even when you are actually in the conversation, it is coming call. The state you know that. Still you know that. That's because it's maybe more a smart system, and we have in that case we have some other state diagram to reflect that thing. Okay, but if this is the state diagram for the traditional phone system, well, dialing tone will have no reaction to any incoming call. Okay, it won't change anything of the system to the system. Okay, yeah. And also, let's go on when you are in dialing. Okay, when you're in dialing state, if other party is idle, you're gonna hear the do this kind of sound. It's kind of old example. Okay. Oh yeah, if you're using cell phone, it's still like do. Sometimes it's music, sometimes it's something else, but it's ringing signal. Or if the other party is busy, it's gonna tell you like sorry, the subscriber calling is busy. Somehow, call again later, or it's go to some mailbox, voicemail. Okay, something like that. Yes, but well, if you're in dialing states, if you choose another incoming call, nothing's gonna happen. Okay. However, if you happen to notice, well, in all of this state, they kind of have a hang up event reaction to the hang up, right? If you are in the dial tone, if you hang up, it go back to idle. In the dialing, hang up, go back to idle. If it's raining, if you hang up, it go back to idle, right? Because the idle is something that always bring you to the hang up is something that always bring you to the idle state. So that information is also modeled in this state diagram. Okay. Yeah, that's what I said. So, like the same event does not always trigger the same event, but hang up always trigger the same event, go back to the idle. I just say does not always, but there are some cases that this kind of events will result in the same state. Yeah. So this is state diagram. It's just a diagram that we have a whole bunch of state, and this state, they change. The system state, they change from one to another. How do they change? It's triggered by event. Okay, it's triggered by event. And all this event, when it's happening, what's gonna happen is based on which state you are in right now. Okay, so that's what I want you to remember about state diagram for now. Now let's go back to the definition. After you look at this state diagram, let's go back to the definition.
Question.
Yeah.
Does those states represent classes?
Yeah, I'm gonna reach there.
Okay.
Maybe today or Wednesday. Let's see if we have enough time. So actually, you're actually associating this with the class. That's a good thoughts. Let me explain that later. State diagram. I see here. So state machines, they intend to describe this, specify this behavior, like transition from one to another. So active objects, that what I just mentioned, active object has its own thread, something that is run independently. They intend to describe or specify the structure and behavior of the reaction systems. So let me answer your question a little bit here. So when we are actually trying to model the state, we are trying to use a state diagram. Okay, it's in a level that it's also, we can still also think about the class diagram, but here the class diagram, we also have this like inheritance, associations, aggregation, these relations in this state diagram. However, this class diagram, instead of calling it a class, we call it a capsule. Another word, capsule. But still, that's a class. Okay, that's a class, but it's active class. Okay, and for each of the class, we will have a state diagram. Remember that? The state diagram is for the capsule or the class. Well, they are the same thing. Class and capsule, similar. Okay, just another name, and some other difference is active and passive difference. Okay, but for every capsule, we have a class diagram. Because if you remember what I mentioned in the beginning, the ADT has state. State depends on the its state depends on the data of the attributes and value of the attributes. Okay. That means every ADT can have a different states, so it can transition from one state to another. And here it's the same, the class, or you can call it class, or you want to call it maybe capsule. Capsule has different state. So if you have a class diagram of all these capsules, student, for example, we have a active class called student, professor, class. The three classes or capsules. If you go dive into one of the class, you should also have a state diagram for that class, which representing how the state changes from one to another. Okay, so active objects or active class. Yeah, and it actually sends message in between to trigger this reaction. between the objects. Okay, so class diagram is like I'm calling the method of another class just by calling, but here in capsule it's a little bit different. It's sending message through the port because if you remember, they have their own maybe thread. Okay, it's not depends on like other procedure to call this class, to call the method. Okay, like I'm a microwave. I'm just running independently on my own thread, and if I receive a message from the door class said open, then I shut down myself, open the door. Okay, so yeah, that's sending message. It's not calling anymore. Sending messages through some port, but still remember. And capsules and relations, they can also have an inheritance, aggregation, association, this kind of thing. And capsules also have attributes, operations. What's special about capsule is it's also defining the port. Okay, port for the sending messages in between. All right. So when you're modeling with capsules, so state diagrams are associated with capsules in UML. Basically, every capsule is associated with a class diagram, with a state diagram. Yeah, capsules are active objects. Active means they just run independently. They more active, have its own thread, something like that. Okay, yeah, example. Like when we're doing interaction here, we are all active, all right? So we're like interacting through the messages. I cannot just call your hand to raise. I send you a message, please raise your hand. I cannot just like internally your brain sending some nerve a signal to like you raise your hand. I cannot do that because my brain is not connected to your hand. I can only send message to you to do that. Okay, that's a good example of active class, active objects. Yeah. However, if I have has a relation, I have a hand. Okay, I can just call the hand method raise up, right? Yes. They interact using message. They have attributes, operation, ports, state machine diagram, state diagram, yeah, and also structure, yes, of course. All right, that's here. State machine. It consists of state. Remember that dialing system, state, auto state. Dialing, idle, this diatone, connected, ring signal, ringing. All of them are called state. That's a condition in which an active object persists for a period of time and behaves in a well-defined way. Okay, just that a state. And the transition is a pass from one state to another. Those connections between state. The trigger are those events which fires a transition. An event represents an incident that can cause progression. And action is the work done when a transition fires. An action typically reads and writes attributes of the instance for which it is executing. Okay, so example is do calculations, generate events, operate timers, read write attributes, like what I mentioned. The state is depends on the value of the attributes. Okay, so when you are actually doing the transition from idle to dial tone, when you pick up the receiver, what happens is some actions actually happen in this capsule. Maybe some attributes may be changed, okay, or some of the method has been calling the behavior of ringing the do tone, okay, dialing tone. These things happen. That's the action. Well, you can see the action that's actually happening here, but it's not represented here. We can see only state transitions and events here. But actually, when you transition from one state to another state, of course, there are some actions being taken. Otherwise, how can that transition happen, right? How does that transition happen? Read and write. Yeah, and the state diagram, well, it shows the state space of a capsule and the events that causes the transition, the actions that result from event processing. It's easy to understand. A state diagram defines the high-level behavior of a capsule. A capsule, okay, state diagram for a capsule. Every capsule has a state diagram. So it's not like every state is a class. No, it's a class have a lot of state. Okay, so it's the other way. And states are rounded rectangles. Transitions are arcs. State transitions are named. Usually it's the events. We use the events to name the transition. And one event can cause different transitions depending upon the state when the triggering the event occurs. Yeah, that's what I keep mentioning. So dynamic, real time. Same events doesn't always trigger the same reaction. It depends on which state is it in. And behavior and state in systems. What do you mean by behavior? The behavior of a system may be said to comprise its response to external stimuli and apparently spontaneous action it takes. So it's just the actions it takes to some reaction of the event. So that's how we define this behavior. Yeah, don't get confused by all this. A lot of definitions here, easy to get confused. But important thing is understand this diagram. Okay. And system behavior is the aggregate of the behavior of all its components as they are interconnected. Okay. We're talking about behaviors, maybe of and capsule. Here, another concept is the systems behavior. It's the aggregation of all the behaviors of all these maybe capsules. They combine for the systems behavior. Okay. So what we're interested in the state models is behaviors is state dependent. Like what I mentioned, everything. It depends on the state, the other input, what kind of output depends on the state. Yeah. And last thing here today, what is state? The state of system is represented by a set of properties whose values determine how the system will respond to the stimuli. Like the ADT, the values decide which state it is in, okay? And more importantly, these values will result in different behavior of that capsule. Like if I am in on state, I keep saying on, there's no method there to be called. If I'm in off state, if I say on, and I'm going to calling the method on. Yeah. A current state attribute is required to keep track of the state in each instance is in. Yeah, current state, of course. Yeah. So, well, if you only look at this definitions, maybe a little bit confusing, but everything is explaining this diagram, state, transition. And you read this diagram, you can read this diagram, you understand this concepts, all right? Like transitions in between, something like that. All right, let's talk about more next time, Wednesday. All right, thank you very much.